So yeah, I want to talk a little bit about a thread of my work that is about going beyond the top 100-ish languages, which is what a lot of people are looking at. So, but you definitely have seen this before, but some recent trends will just use BERT or these big pre-trained language models for everything. And if we go beyond English, like I guess Kenton told you earlier this week, then you can make it multilingual, right? You can take data, say, for 100 languages, like several people have done, maybe do some upsampling or whatever, and now you have a big model that has seen 100 languages. And these will be, at a minimum, a really good starting point to do all of the downstream NLP tasks that you might care about. But as you probably already know, if you speak any language other than English, these don't work equally well for almost any task, really, across the world's languages, right? So if you think about not accuracy itself, but about the utility that we produce with our models, then I think you will all agree with me that we don't produce equal utility across, for everyone. If you compare, for example, an American English speaker and the things that they have access to, from navigation in their own variety, they can search the web. They can, an American English speaker can basically do everything we can do with AI. And then think of an Arabic English speaker. Does anyone speak Arabic here, or maybe? No. Okay. So and then you might have seen a lot of papers on Arabic, but then none of the academic work that we do. Okay, not none. A very large chunk of the academic work that we do on Arabic is not on the Arabic that people speak, right? Because no one really in their everyday lives speak modern standard Arabic. They'll speak their normal their vernaculars like Tunisian Arabic or Egyptian Arabic or whatever. And then you can also go and think about the millions of speakers of, say, African languages like Bemba in Zambia that cannot do anything online with their own language. Right? So here's an idea. Maybe we can quantify the utility at the global scale. And ideally, what we want to do is be able to quantify this for every person in the world. And this could guide our research, right? Because I think that why we're doing research is in order to produce societal value, hopefully at the global scale. So what if we could measure utility for every person in the world and sum it up and have a metric that tells us the model that you built is, giving that much utility to the world, and the other new model that you built is going to give, an extra boost in the total utility, right? Obviously, there's problems in doing something like this. First, how are you actually going to measure utility? Because we cannot go asking people, hey, how much utility do you get from this product versus this other product, right? So it's very hard. So let's say, for the argument's sake, that we can correlate utility with accuracy. A really, really, really good system will have really high utility. A mediocre system will have mediocre utility. And although, things are not linear for sure. Like people won't like to use a mediocre system until it's actually beyond a certain threshold of accuracy or generally quality performance. The other problem is, how do we go to every person in the world? So obviously we cannot do that. So let's say we are going to instead measure over subgroups, and a natural group to group people into is their languages. So instead we can take this metric or whatever and use some sort of demand for a given group for a language L, and then some sort of utility measure for that particular language. So if you have that and you sum over all of the languages, now you have a measure of, or some measure of, the global utility, or how much good you did in the world, right? And I have this normalized demand here because there's different ways that you can view demand, right? You can say, I want to build models that are equally good for all languages in the world. So you care about some notion of linguistic equity, so that all languages get hopefully equal performance or equal utility to all of their subgroups. Or you might care more about the people themselves. So you might have some sort of like demographic utility, so that you think about, how many people you're actually affecting with your work. So this is a tau parameter that you can play with to get this demographic or linguistic average utility. I kind of delved straight into this, just basically to tell you that there's a very simple metric that you can use to measure or show how different things are. But the super specifics don't matter, but I wanted to show you how different things look when you go beyond English or even beyond the top N languages in the world. So if you zoom in and you look at analysis tasks, like, a bit more esoteric NLP tasks like syntactic analysis or morphological inflection, the word level, and you look at how well systems perform across the world's languages. When you create a plot like this, where the x-axis is the number of speakers per language, and the whole x-axis is, say, the world's population, and each bar for the language is proportional to the language's population, and the y-axis is utility or performance in this case, you can see very interesting things. So, for example, in these esoteric NLP tasks, if we have data in the language, we can do pretty well, okay? And the metric that I presented is the psi, is the colored thing here. And ideally, we would be able to cover this rectangle for all of the speakers of the world with high accuracy for everything, right? So the interesting part here is what we're missing. All of the basically millions of speakers and thousands of languages that we cannot even measure, because we don't have test data, let alone training data or anything like that, in order to build systems. But the main takeaway from this is that, at least for these more esoteric NLP tasks, if you do have data, then most likely you can do these tasks very well. The problem is, do these tasks actually translate to real world utility? These days, I think yes. But something to consider. Then looking at more user-facing tasks, things that like question answering, that it's something that people do on their phones every day, or speech synthesis, which can be very, very useful for the thousands of languages that are predominantly oral. Now that curve is different, right? So we only have decent performance or good performance for just a handful of languages, like English, Spanish, maybe German. And there's languages where we might have data, but we cannot perform these tasks well. And then still, there's even more languages and speakers that we don't cover, at least with our popular NLP data sets. And then if you go even further in machine translation, where have pairwise tasks in like two pairs of languages, the story is very different depending on the language that you look at. If you look at translation into English, you get coverage for many, many, many languages, and decent for a lot of speakers. If you look for MT into Spanish, you get coverage again for many languages, but maybe less good models. But then if you look at, say, machine translation into Bengali, then you have terrible systems, like not usable. Like these speakers, they still don't really get any utility out of the systems, even if they exist. Okay. So the nice thing about this whole thing is, we can have a metric that can guide us, because you can think of, when you look at these graphs and knowing that there's, the same amount of speakers for Bengali as German. Should you work in German or Bengali? For me, the answer is plain. That you should work on Bengali, because there's a lot more utility to provide to the world. Okay, so so I hope I have convinced you that there's definitely still a lot of work to be done. Yes, Matt.
Just to confirm my understanding, so the x-axis is basically
all speakers in the world. Yes.
Okay, so
grouped by language.
And is this any speaker of a language or L1?
Sorry, what?
Is this L1 speakers of a language?
L1. So it's basically based on ethnologue data, because it's not probably super accurate, but that's the best estimation you can get. So yeah, it will be L1. There's no L2 speakers, of course, would be a different story.
Okay. So I'm actually kind of surprised by this off the left. I haven't thought about this question, but this says that 80% of the world or this 80% of the people in the world can translate their language to English. I'm just guessing.
Right.
Okay.
I mean, it's not super surprising, right? Like if you think of like 1/7 is Chinese, so you have a good system for that. Then maybe 1/10 or something is, or maybe less, is European languages. Then there's all the Spanish speakers in South America and Central America, in the Americas. So yeah, but then also if you think about the 100 million, 90 million of Bengali speakers that have systems, but they're not nearly as good as the German speakers.
And is this just 100 languages?
No, that's no, it's more than 100.
I mean, the ones you have data for.
For MT, we are closer to 180 or something. It doesn't include the latest NLP work out of Facebook, but yeah. So I don't know if it would make a big dent though, because here the x-axis is proportional to the population. So if you add the 10,000 speakers or 50,000 speakers that speak Ligurian, it would be another graph, but it would make a big dent on the population demographic. The utility. Yeah, Jason.
I'm just curious what the relative quality metric is.
Yeah.
And whether that metric makes sense when you're translating from a language to itself in far left.
Oh yeah. So the idea here is that we wanted to have the x-axis comparable for all of them. So the idea is that for English speakers, you don't need translation into English. So they already have that utility. So and the same for here, like Spanish speakers don't need this, so they already.
Yeah, no, one hypothesis about what you're doing is you're looking at the ratio of the blue score when you translate from German into Spanish.
That's exactly what it is.
Spanish into Spanish, but when you translate from Spanish into Spanish, you're actually using a paraphrase rather than.
No.
So you get 100% blue score when you.
Yeah, the idea is like if you translate from Spanish to Spanish, you get 100 blue score.
Okay, so we could actually interpret this as absolute, as a blue score. You say relative.
Yeah.
It's actually absolute because you're always dividing by 1.
Yeah. Well, no, you're dividing by the best system that you can have.
But the best system is probably just copy the input.
Well, relative quality for all the other speakers. So there's details on the paper, but this is relative quality to the best system, which in fact it would be like the Serbian to Croatian system or something. That's like a blue score of 70 something.
So sorry, are you saying that the Spanish on the left is translating between dialects of Spanish?
No. So what I'm trying to say is that this notion of relative quality is very hazy, and for MT is even worse. So what we used for the paper is a normalized blue score, where the normalizer is just the maximum blue score that an MT system got in the data set between any language. So that was close to 70-ish.
Okay, and in Spanish to Spanish, why didn't that end up doing even better than that 70-ish? You only show 1 point on that, so I can look at the paper.
Yeah. So for Spanish to Spanish, we don't do that because you assume you don't even need to go through the model, right? You don't need to go through the model to do Spanish.
I'll look at the paper.
Okay. Yeah. We can talk about it later too. Yes.
Sorry.
Yeah.
Maybe it's in the paper. These are all relative metrics.
Yes.
So I mean, it could be that MT doesn't work at all, actually. So when we interpret the plot, it's how well it works relative to the best system.
Yes.
Is there for the other tasks like MT, it's fine to have some notion. For the other tasks, you write there's some notion of like user study where if the performance is above this metric, we consider that it works.
So there are some a couple of papers at Chi that give you some sort of threshold, but you can kind of get this. So okay, let me give you an example. We have ways to do zero-shot stuff, say for question answering, right? Why are these not deployed by Google or Amazon, right? They don't meet a certain threshold.
Yeah.
So there are studies, some of them published, that give these type of thresholds of what accuracy is good enough to deploy for people. We don't use that here for cases where the metric is nice between 0 and 100 or 0 and 1. Then we just use that as the perfect utility would be a question answering system that always gives you the correct answer, right? So it's just that MT is super weird. I don't have a good metric for the actual utility. So if anyone is interested in exploring ways to tie automatic metrics that we can scale to many, many languages to actual utility for people or users, I would be very interested to talk to you. Okay. But anyway, what I want you to take away from this plot is that there's still a lot of work to do when it comes to all the others that we really still don't cover for basically almost, for every task. And you can go even deeper, right? You can think of, well, okay, question for anyone who wants to answer. What's the difference between a language and a dialect?
A language is a dialect with a harmonic.
Yes. Okay. So thank you. People at other universities don't get that answer correct right away. So no languages are monoliths, and you need to be able to model the different user variations. This is my favorite map of Italy. You can see that all of the models that we built for Italian really just cover what you would call like modern standard Italian, which a lot of the young people use or are forced to use in some spaces, but still at home they would be speaking with the grandparents, the local varieties. And a big problem here is that almost all of them are really spoken, right? No one in Italy really writes Ligurian or Sicilian, or maybe they write Neapolitan because they're proud of them, proud of their language. So if you, like all of the graphs that I showed you before, a lot of them are not, don't even take that into account, this idea of language variation. So we need to be able to go deeper, right? So in order to do that, we started thinking about building data sets that go to that more fine-grained level. And I wanted to give you an example of what we did. So we built a question answering system, a question answering data set, built on top of Google's TidyQA. So now the idea is that we are going to have question answering in the setting that most people use it. You have your phone or a Google Assistant or Siri or Alexa or whatever, and you ask it, how tall is Usain Bolt? But you ask it in your own language and in your own variety. So we took the data from TidyQA, had them recorded in many, many varieties. So we had something like 11 Englishes from throughout the world, from like South Africa, Nigeria, Scotland, India, the Philippines, and so on. Or we had 7 Arabics. You see here in the green markers from Morocco to Egypt to Saudi Arabia and Kuwait. And we also had a couple of other languages. So we had 2 Bengalis, a Bengali from India and Bengali from Bangladesh. We had Swahili from Kenya and Tanzania. And we also had Korean, but from Seoul, or from Southeast. And we recorded audio for all of these questions. And you can see the differences. So the idea now is you have audio, you transcribe it, and then you put it through a question answering system. If you had perfect transcription in all of these varieties, say for Arabic, you would get something like a 51 F score, okay? Not great, not terrible, right? If you look at the actual performance, when you now break it up into the different Arabic vernaculars, you'll see that people in Algeria, DZA, get the same as they would if we were using MSA, but people in Egypt, they get like 7 points less, right, in terms of the utility. So Egyptian Arabic is not handled as well by our systems as Algerian Arabic. So now you could make an argument about how based on these measures, right, Algerian speakers are more privileged than, say, Egyptian or Saudi Arabian speakers. Or it's the same for Kiswahili, where now the distance between the gold text, using the gold text versus using the ASR automatically transcribed text is even bigger between the Kenyan and Tanzanian Swahili. Yes?
Do you have any intuition of how much variation there's between people? So like,
oh, a lot. Oh, it really depends on the language, right?
Okay, yeah, but if you had 2 people from like Algeria, like would they get as much of a variation as Algeria?
Oh, I mean, these are all like multiple people in each sub dialect. sorry, so in each dialect we have like between 7 to 20 speakers. Yeah, and then of course there's a lot of variation, right? Obviously, if you go to Algeria, then you will get different varieties if you're at the bottom of Algeria in the Sahara Desert versus if you're like at the Berber regions in the north. So
Well,
yeah.
there's other individual variations beyond dialectal.
Oh, of course. Right. Yeah. I would assume that, ideally, you could be able to handle also all these individual variations, but I'm assuming that, we're not even doing the dialectal stuff. So when we can handle that, then maybe we can handle individual variations.
I think the question is just what are the error bars on the individual numbers that you have there? Like if you look at differences between men and women, they're tiny when you compare to the differences among individual men and among individual women.
Right. But we actually have gender balanced data sets for that. So we can actually break the data set also by gender. Yeah. Yes.
Can you talk about how you reported data?
Yeah. So we hired a company that had access to speakers in all of these places. And
were the conditions pretty normalized across all the different dialects? Because then the ASR, just the ASR transcription quality
could matter.
from the acoustic channel or
Yeah, so they are all. So we used Appen, a data collection company, and they have their own app that they use. So almost all of them are collections done in a modern smartphone. So at least it matches the use case of asking an assistant on your smartphone. And we did have a quality assessment on top of that. So if there were recordings that were super noisy or whatever, we re-recorded them. So the data set's fairly clean, but it's also smart for recordings, which I don't mind since that's realistic. We used the publicly available Google's ASR systems that they can be specialized by they can be localized by language. Often the localized system doesn't work as well as the generic, say, Arabic system or the generic English system. I have the results in the paper, but here I'm just showing you the best results we got for each variety. Right, and then when I'm going to show you these graphs that are basically the same graphs that I showed you before, but now looking at the effect of the dialects. So you can see again how, say, in Swahili, there's a distance between written coastal Swahili, but really how you would normalize all of the dialects into one written form, well, the coastal dialects versus what people actually speak at the bottom. Okay, so let's say now, let's make a plan, and how are we gonna actually scale and be able to cover all of these, beyond the top 100 languages? Because you might have seen the idea that, okay, we're gonna make these highly multilingual MLMs, masked language models, or just language models. We're gonna train them on the 100-ish languages that we have data on, and then we're gonna take them and apply them to all the other languages. And then when you try and do that, you might get some numbers, but then there's a big disconnect between what you actually trained on and what you're trying to apply it on. So these 100-ish languages that you have used, they're, these dominant languages, they're all written standardized languages that almost the vast majority of them will use the Latin alphabet. And they're all high-ish resource compared to all the other languages, local languages that are oral, predominantly oral. They're non-standardized. So even if you get written text, it will be, in different orthographies, or even if it's the same language, the same, say, alphabet, or the same writing system, you might get 3 different conventions of how people just write the same sound or the same word. And of course, they will be very, very low resource. So the first question to ask is, well, okay, out of these 6,400 languages, ish languages that you haven't seen, are these equally hard, right, for us to model? And the answer is, we can try to answer this, and I'll give you the setting on how we went about this. We took a bunch of languages that were not seen in the model's pre-training stage. So say for multilingual BERT, right, it has not seen Bambara or Wolof or or Faroese or Maltese as part of its pre-training regime. So we have all of these languages, and we are going to try to do our best in 3 tasks: part-of-speech tagging, dependency parsing, and NER. Okay, and then we're going to see how we can categorize languages. So how can we get a language model for all of these languages? Right? Here's option 1. We can use whatever text data we have in these languages and train a monolingual language model, say like a Faroese BERT or a Maltese BERT. Okay, or we can take MBERT as it is and try to perform the task in a 0-shot setting, or something that I'm sure you'll all say, why are you going to do option B? But if you do option C, is the other thing. You can use whatever data you have in the language, do continued pre-training, train with masked language modeling or whatever on the multilingual BERT, so that you basically adapt it to the language that you care about, and then learn the task and perform the task in that language. Okay, so there's these 3 options for now. I'm gonna go back to adapter units that you might have heard of a little later. So if you do that, okay, and now you compare all these 3 options, then some languages behave very different than others. There are some languages that are what I would call easy. Not easy as in we can perform the task right away super well, but basically the multilingual model, because it has seen closely related languages in its pre-training stage that also use the same script as the languages that you care about, then you will do a lot better than a multilingual using you can do it a lot better with the multilingual model than using a monolingual one. So let me tell you how to read this. If we train a Faroese BERT and we evaluate it on, say, part-of-speech tagging or dependency parsing, then you get some numbers in number 1, right, or number 4. If you use MBERT in 0-shot, then you already get better by just 0-shot, right? It's better than training a model specialized to that language with whatever data we have. But if we do this continued training, you can do even better on that language, right? And the reason for this is fairly straightforward, right? Multilingual BERT has seen a lot of Germanic languages, has seen Swedish, German, Danish, Norwegian, right? And so it can basically 0-shot, it can produce good representations for Faroese. And it's same story for Swiss German, again, because it has seen High German. You could, if you like Swiss German, so High German speakers cannot understand Swiss German speakers. Philip can confirm, at the written level, it's fine. You can get decent representation for Swiss German with multilingual BERT. Some other languages are, let's say, intermediate, as in multilingual BERT in and of itself, without the extra fine-tuning stage, is outperformed by strong non-contextual baselines. But if you do this continued fine-tuning on with whatever text data you have in the language, then you get better models that are also fairly usable. So say for Maltese, you'll notice that the baseline, which is static embeddings trained on the same data as a Maltese BERT, okay? The baseline performs better than the Maltese BERT. But if I take multilingual BERT and do continued fine-tuning on the little Maltese data that I have to produce a model tuned to Maltese, then we can outperform all of the baselines and produce decent systems. The same for a couple of other languages like Bambara or Wolof. Yes? To the easy languages?
Easy, but the German cost numbers look really bad compared to like Wolof crystals. I'm a little surprised.
Right. So yes, but I categorize them not based on the absolute numbers, but based on whether you should just use the multilingual model or what is the best way to use a multilingual model versus it's actually better to use a baseline, a monolingual model trained from scratch. Maybe the easy and intermediate are not the best labels to put, but let's say they're easy for the multilingual model. And yes, they might be, I mean, first of all, they might, I don't know if they're like necessarily comparable, right? Because we're working on the UD data, at least for parse tagging and dependency parsing. And it could be that you have easy data like easy test set there.
Yeah, I guess that was sort of my question. That like even categorizing them this way, you know that it's a function then of the language or just the data that you have available. Like maybe the trend inverse even for other languages if the data is biased in some way for certain languages, which is less.
I mean, it has to be a function of the data that are available, right? Both for training and for testing. But that's all I can do for now, right? And it's also a function of the model that you use, right? So we did try it also with XLMR, but the stories were more or less the same between XLMR and MBERT. But I don't know how I could do better unless I had a massively parallel.
I was just asking about the data, I guess. Like, what's the difference between German and this one? It is fine.
I mean, yeah. Yeah, so I think the most interesting class, sorry, Jason.
So I'm a little confused about the relation between lines 1 and 4.
Here
these
or
and the previous ones, yeah. Is the fine tuning on line 4 being done on this exactly the same data set as the baseline model?
Yes.
Was trained on?
Yeah.
I see.
Yeah, so we have a set of text in, say, Maltese,
Yep.
and we either use it to train static embeddings, or we use it to train a bird, or to do continued fine tuning.
Yeah. Okay, yeah, so I was just surprised at how small the improvement was on the last line of the next slide. Here it's huge.
Oh, right.
Yeah, but if,
Right.
if you go back to the other slide, it looks like over the baseline, like
By
you're
a little bit.
95.99 going up to 96.4. Some of the others you did a couple points, but 92.3 to 92.6. In fact, actually,
It might be.
hurts in the final column.
Yep. Yeah.
Um,
And then that continues also if you go into the hard languages.
Yeah.
Hard are the ones where the non-contextual baselines, the static embeddings that we can build off of our little data that we have, are better than anything that we can do with contextualized models. So, for example, in Uyghur, or depending on the task, right? But in part of speech tagging, the static baseline is better than multilingual BERT or anything that we were able to do. And it was the same. I'm not going to show you more. They're on the paper. There's also the same for South Sorani, South Kurdish, or for Sindhi and all that. And the interesting part is that for Uyghur, Sorani, Sindhi, the model has seen related languages. Okay, all of them. So Sorani and Sindhi are in the European. If I'm not mistaken, Uyghur is Turkic. They are included. There's related languages including in the pre-training of the model. So we asked, why are these languages hard? Yes.
That's right. I'm just still surprised. I think the difference here between line 2 and line 4 is just initialization. Is that right?
Line 2 and line 4?
Maybe there's architectural differences as well. So maybe MBERT is a lot bigger. It just surprises me that random initialization gets 77% in the second column, and informed initialization gets 49%.
Yep.
Is initialization the only difference between these two, or is the MBERT model?
I'm pretty sure that it's the only one. There's a small chance that the Uyghur birds is smaller. Also, so we might have. I'm not accomplished sure. It might have fewer layers. But that would be the only thing, really.
I guess there's also a question of stopping conditions.
Yeah, but but you're right that the random initialization is doing better. What do you mean by starting conditions?
Stopping conditions.
Oh, stopping conditions.
How long are you trying for?
So I'm pretty sure the Uyghur bird was trained for slightly longer because you start with random weights as opposed to the informed ones. Yeah.
So maybe it was just too hard to forget the MBERT weight. That difference is just.
So honestly, we can do better with MBERT. And I'll get to this. It's basically the big difference is that you start with a predefined vocabulary when you start with the pre-trained MBERT. And that's an issue for languages. I'm going to get to my next slide. And that's an issue for languages that use different scripts than other languages that we might have seen during pre-training. So for all of the languages that that thing happened, like as in the static embeddings were better or whatever, or maybe the monolingual model was better than the multilingual one, where languages where we might have had related languages during pre-training, but they were using different scripts. Okay, so we did test this by employing transliteration. So for the Uyghur example again, we took all of our data. So Uyghur in the data that we had was written with the Arabic script. Okay, and we Romanized it, all of our data, including our monolingual data that we used to pre-train or continue fine-tuning, and the test data that we have. Okay, and now you will notice a bunch of things. Regardless of whether you train an Uyghur bird on the same data in the Arabic script or the Latin script, you get similar numbers, right? For almost all tasks, you get 87, 86 for part of speech tagging, 57, 54 for dependency parsing, and so it doesn't. The script doesn't really matter in a monolingual setting. But now even like mbird in and of itself, without any continued fine tuning, you'll notice that in part of speech tagging we jump up from 77 to 87. Or in dependency parsing from 47 to 65, right? And I suspect that the reason for this is that the largest data that we have in Turkic languages is in Turkish, and then maybe Azerbaijani, and all of these use the Latin-ish script to write their languages, right? So the moment I make Uyghur look a bit closer to what the model has seen, now I can handle it much better. It was the same, say, for Sorani and for Mido-Mari, right? A Uralic language where we transliterated it from Cyrillic to Latin. Again, why? mbird has seen Finnish and Estonian and Hungarian, which are all written in the Latin script, but it hasn't seen any Uralic scripts written in the Cyrillic alphabet. So that said, just Romanization is not the solution for everything. Okay? If you take Mingrelian, a Kartvelian language spoken in the Caucasus region, the most related language to it that the model has seen during pre-training is Georgian. And Georgian uses the Georgian script, as does Mingrelian. So if I change Mingrelian into Latin, now the models do worse. So I guess the takeaway is think about the language and what might work better for them. Yes?
Are you manually transliterating these?
Well, we have models, not as in.
I guess what I was saying is like, how do you separate, like, treating that as some pre-training later in the model versus that actually being a separate, like, if that is a separate model, could you just not include that in the larger model for this downstream task? Like, if you're going to be, like, what exactly is the transliterating doing as being a separate thing versus just like the first layers of the model? Something it does is translate everything into a Roman script.
I don't actually understand the question.
It does affect compensation, which was turned out to be important for the answer of my question.
So yeah, that's the big change, right? That from the get-go, the representation that you use in the input are very different. Yes. Do you have a question or okay?
Well, I will ask one actually. So wouldn't the Georgian to Latin problem be fixed if you Romanized everything before training mbird?
I guess. I'm not advocating for this, but I guess.
It doesn't have to be Romanization for the idea.
Yes, yeah, and we actually are thinking about this on a project with Kenton. But yeah, and this holds also in high resource settings, right? So if you Romanize, say, Arabic or Russian or Japanese, then models become worse. So something, and also you could argue that transliteration in of itself is not the best way to represent things. But yeah, something like IPA, I think, would be a really good idea. So, okay. So now that basically my takeaway for this work, I want it to be that you got to look at the properties of the language, or even things that we rarely think about, like the script that is written in and how it relates to the languages that the model has seen before, and be careful in your choice of transfer languages or what you're doing. Okay, so I'm gonna talk very briefly. I actually don't have you're gonna let me know when we're supposed to be done, okay? So because that.
We're maybe 10 more minutes.
Oh, dang. Okay. So there's ways to do better by further incorporating some linguistic information. So what I didn't tell you before is that there's another way to adapt a multilingual model, and that is to use adapter units. So here's how this works, right? So let's say you have your whatever BERT model, right? I'm gonna remove all of the arrows and make it look nice. So you have this BERT model, okay? And what you can do is insert little units between all of the layers, not just between the first and the second layer, between all of the layers, that when you adapt to a new language, you only train these units, right? You freeze the rest of the model and you use these units to adapt your representations between layers and all the way to the output so that they work for the language. The advantage of that is when you don't have a lot of data, you only have to train these few parameters of these units, okay? And you don't forget what the multilingual model has already learned, right? So you can insert an adapter unit that will be specialized to English, because why not? You can use that and also train an adapter unit that is also specialized to a specific task. And you can merge them, not merge them, like stack them between all the layers and use that model to do entity recognition, say in English, okay? You can do the same thing with another language. You can take, say, Bengali data, train a Bengali adapter with, for example, MLM, just mask language modeling, assuming you don't have labeled data for any specific task in Bengali. But now you can do something very nice. You can take that part of speech tagging task adapter, and you can stack it with a Bengali adapter. And now you have a Bengali part of speech tagging model. That actually works, okay? It works decently well, almost as good as fine-tuning the whole model, okay? So we can do zero-shot adaptation to new languages at a low cost. The low cost are these additional parameters that you need to train. It avoids the catastrophic forgetting, so you can still use the model for all the other languages. And you get performance comparable to full model fine-tuning, okay? So the question is, can we do better? And the answer is yes. So all of these little adapter units in the standard setting so far were just trained for each language individually, right? But if you want to train, my example would be go back to Europe because I'm more familiar with it. So let's say you want to train Catalan, Asturian, Valencian, Ligurian adapters, right? And you only have a little bit of data in each of those languages. Okay, maybe for Catalan you have a lot. Then is there any reason to not leverage the fact that all of these languages are related? The answer is actually, that's what we're gonna do, okay? So we're gonna stack adapter units that share parameters between languages at different levels. So we can have, say, an Indo-European adapter with parameters used for all Indo-European languages. And then we can have a Germanic adapter with parameters used only for the Germanic languages and not for, say, Romance or Indo-Aryan languages. And then on top of that, we can have a language-specific adapter. Okay? You could go even further, right? You could say, oh, I have English. And then you can, if you wanted, if you have data to train those adapters, you could say English from the US versus English from the UK versus English for Kenya and have further variety, say, adapters on top of the language adapters. So if you do that, then during training and during inference, you just follow the appropriate path through this tree, right? So say if you have a Dutch input that you want to either train or do inference on, then you'll follow that path through the model. Okay? If you have Bengali input, now you're going to use that path through the model. Is that clear? Okay. So we do that. We trained all of these adapters with all of these parameter sharing on a lot of languages and multiple language families and all. And we evaluated them on several languages. So I'll just go straight to the results. Here we did again, we did a bunch of tasks in the paper, but I'll just show you dependency parsing results. If you only use essentially a task adapter, equivalent to just learning the task in a zero-shot setting, say by training in English, then you'll get these numbers across, let's say, 12 Germanic languages. Okay, these are averages across multiple languages per family. If you use language-specific adapters, like and the task that you learned, the task adapter that you learned, say by say in English or Estonian for Uralic languages, then you will do usually better. Okay, Germanic ones are weird in the setting that most of them are seen during pre-training. So these are our baselines that don't do any parameter sharing at the level of the family or of the genus for each family. And if you do what I showed you before, by organizing the adapters according to the phylogeny of the languages and having a bit more informed parameter sharing between them and train them all together now in this tree, you will do better for most of the languages that we have here. And more interestingly, that gap really increases when you focus on the languages that were not part of the pre-training of the model, because these are the ones that are more interesting, because these are the ones that you actually need those adapters in order to perform well. So if I break this down, now you'll notice that I only had 3 Germanic languages that were not seen during pre-training, whereas I have 8 small Uralic languages that I hadn't seen during pre-training. And I am also showing you here results on Tupian, 8 Tupian languages, a family spoken throughout South America, like Paraguay, Brazil, and so on. And you'll see that now the gap is generally bigger. Okay, so for the 3 unseen Germanic languages, we went from 52 or 50-ish to 60-ish. For the Uralic languages, we have a big jump. For Tupian, for some languages it gets better, for some languages it gets worse. It's super hard. I think we have like maybe 10,000 sentences in each of those languages, and the predefined vocabulary, I think, of multilingual models is an issue in this case. Yes.
Was there any study on how the phylogeny affected this? Like if you gave it a random one?
Yes. So in fact, you could argue. So the takeaway from here is that you get larger improvements in the languages that actually benefit from this parameter sharing, the unseen ones. So yes, you're absolutely right. So there's 2 things that we need to disentangle. One is the actual phylogeny, using the phylogeny as opposed to say random trees, organizing the language in random trees. And you could also say, hey, hold up, the baselines that you're using use 1 adapter, right? The language adapter. Your models use 3 adapters, like the family, the genus, and the language adapter. And you'd be fair. So we did this ablation, right? So on average, I'm only showing you results on Uralic languages, but these hold up across others. The thing that this is the improvement that you get by using the family and the genus and the language adapter. And then what I'm gonna do is I'm gonna make these parameters smaller by 30, make them like 30% of what they originally are. So now this FGLD constraint is a setting where I still have this stack of parameters that are shared according to the phylogeny, but the total number of parameters is equal to having a single language adapter. And now we're still getting nice improvements. Okay. Here's another problem. You could say, well, you have 3 adapters, so you have made your model, your neural network deeper, right? And we kind of know from the deep learning literature that deeper models are better than shallow, wider models, right? So we can compare to these 3 adapters that don't do any parameter sharing between languages. So I can stack, say, 3 Dutch adapters that are smaller, and each of them add up to the parameters of a single big Dutch adapter, and compare to that. And basically, that doesn't make any difference between you see the first column and the last column. And the parameter sharing actually matters. So it does help, okay? The thing with the random tree, I don't have it in the slides, but we did try it in the paper, and it does, as you might imagine, the phylogeny informed tree does better, okay? So these are results on dependency parsing. We also use this for MT in our submission for the large-scale multilingual systems for African languages. And we got the 2nd place between the constrained systems. Yes?
Yes, there might be one other factor.
Mm-hmm.
I assume in the tree version,
Mm-hmm.
you have a lot more data for like the Indo-European layer.
Mm-hmm.
For the language-specific ones you only have. I mean, it's an advantage of using the method. But do you think that's the improvement, or is it that it's learning?
So yeah, you have leveraged, say, all of the data from all Germanic languages, right? To train both the Indo-European, a bunch of other languages, and the Germanic adapter, right? So now I think it's dual thing. First, you see more data, but now the Faroese adapter has to do less work. It only has to model the differences of Faroese to the other Germanic languages. Because in theory, the Germanic adapter captures the peculiarities of the Germanic languages, right? We haven't done anything fancier like trying to make the adapters specifically learn these things, like capture the differences between the language and the families or something like that. But I think it's something like that, right? So with a few amounts of data you have for that language, I think it's easier to start from, say, an informed Germanic adapter and then just have to learn a little bit about Faroese rather than getting to there from scratch. So, okay, I'm gonna run through my slides. Yeah. So yeah, basically, on the large scale, the large scheme of things, I think we don't need to only have monolingual models or massively multilingual models that share everything. I think we should go into basically somewhere in the middle. It's great to have multilingual models or say universal parameters or whatever, but you do need to be smart about how you share the parameters between languages. So this takeaway, I was going to talk a little bit about how we can actually go into all of these languages and what data you might want to use. So I personally believe that, just few shot is the way for all of these languages. We're never going to have a ton of data for all of these languages. And there's ways that we can deal with a vocabulary mismatch issue. There's methods like Canine from Google or ways to modify Embert's vocabulary to go ahead to modify it so that you can better handle those languages. But I do believe that we can do just as well for all these languages with a little bit of data. So what I do think you should do is think a bit about the data that you might be using or collecting, right? So how much data should you use? Basically, my argument is that in this paper that if you have decent baselines, then you should spend your budget across multiple languages. I think that's important, actually. Give me just 1 minute on this. So let's say you want to do question answering, right? And you want to build a system for as many languages as possible, right? Initially, what we focused on is take a lot of English data, right? That we can use to do zero shot. But if we had a constrained budget, I'm going to skip this. If you had a constrained budget, say you can only annotate 4,500 examples, right? How should you split this so that you do better across languages? The answer is as equitable as possible, right? If I spend all of my budget on English and then care about evaluation on, say, 6 languages total, then you might get this. If I split this budget across 3 of the languages, now on average, I'm going to do better across the 6 languages. If you further split it on all the languages, you're going to do also even better, right? So I think you could keep going further and further up to an extent, because really in the previous slide, basically, I will show you that with just something like 400 examples per language to train on, with good baselines and good ways of doing cross-lingual learning and cross-lingual transfer, you can get within like 90-80% of the skyline that uses thousands of training examples in that language. Okay, great. So that's all I have. Well, there's also questions about how representative are your data of the actual speakers that you're trying to model, which is super important, I think. So you got to think about where does your data come from and which speakers are modeled. So if you think of an English data set, which English? It's not going to be Nigerian English, I guarantee you, or Kenyan English or whatever, right? So we have some work on trying to visualize this and do some interesting stuff, and I'd be happy to talk about this later. So yeah, the only other thing that I'm going to say is I think you should, if you end up working with communities, especially indigenous communities or endangered language communities, it's super important to think and know what they need and what they want. I started my career during my PhD wanting to do NLP for endangered languages, and we're like, we're gonna do translation. Turns out, if you think about this, they don't really need translation. Most of the people that speak those local languages are also bilingual or multilingual in whatever is the dominant language of their region, right? What they do need is translation systems or NLP systems that can handle their own variety of the dominant language, right? For most things. So what NLP things do they need in their own languages? The answer is very basic stuff, right? So I've done some work in Griko and in Mapadungun where they cared a lot about building applications that are useful for education. So for Mapadungun, they really wanted to be able to show learners of the language what the proper segmentation, morphological segmentation is, or the possible segmentations are, because Mapadungun is polysynthetic really, and it's not easy for new learners to figure out what a big 40 character word means. What word? Okay, so or they might need tools for transliterating or normalizing their writing systems, because almost all of the languages that I've worked with, like Mapadungun or Pomak or Griko, for example, they will have like 2 or 3 different writing systems, and they're going to have data in each of them. So to use them in educational settings, they need to have a way to search with whatever writing system each person prefers, and search over them and find examples in all of them, or to normalize them, normalize them in all of them. So I'll be happy to talk to you about later in our meetings about actually working communities. Sorry I didn't get to that earlier. Thank you. Oh, fun fact, it's International Translation Day today. And there's a UNESCO event that you can just attend online. I think it ends in a couple of hours, but still, there's interesting talks about translation and interpretation in indigenous languages.
Thanks. If you have any questions, I think probably due to time, it's better to come up and ask.
Yeah. Really sorry, I have no timer here. I don't know. Yeah. Sorry to keep you waiting. All right, thank you. What time is it?